The second type of chromatography that we use is the high performance liquid chromatography. High performance liquid chromatography uses high pressure to force the solvent or our mobile phase through a packed stationary phase. Previously, high performance liquid chromatography used to be called high pressure liquid chromatography, and then it has been changed to high performance liquid chromatography because it uses high pressure to force the solvents through the packed column or the backed stationary phase. The This type of chromatography offers some advantage over gas chromatography. Although gas chromatography may be preferred by many people because of the cost, because gas chromatography is much cheaper compared to the HPLC. But the some samples or some analytes are not volatile enough to be used in gas chromatography. So the only way to use it in chromatography is through the use of high performance liquid chromatography. The different components of the HPLC, there will be a video I'm gonna leave for you that that will show you the different component of HPLC and the operation of HPLC. So please have a look at this video to familiarize yourself with how HPLC works and the different component of the instrument. The chromatographic process in itself. The type of column we used here is the packed column. We don't use the open tubular column like gas chromatography. In gas chromatography, we can use the open tubular column because we use gas phase in the mobile phase, and we also use the our analyte or our sample as a gas. So it can diffuse easily and quickly into the stationary phase. But the liquid here diffuses, which is the mobile phase in case of HPLC, it doesn't diffuse quickly. So it's much less, it's much slower in diffusion. So it will, we cannot use the open tubular column. So the column must be packed column. And the efficiency of our column will increase as the particle size of the stationary phase decreases. So the packed column stationary phase, of course, the stationary phase can be either a liquid that is covalently linked to the solid, or it can be a solid directly, but it must be packed and it must have some solid support. So the smaller the particle size of that solid support, whether it's directly the stationary phase or it's just a support for the liquid stationary phase, the smaller the particle size, the better the efficiency of our stationary phase. The typical particle size here is between 1.7 and 5 micrometer. So the smaller particle size is better because it gives you higher plate number. And we talked about the efficiency of the column, the efficiency of the column, the chromatographic column before, and we said that the higher the plate number and the shorter or the smaller the height of the plate, the better or the efficiency of the column. So the smaller size will give you a higher plate number. But then at the same time, it will also give you a shorter runtime and lower detection limit. So it has many advantages here. But the only disadvantage here is it will need higher pressure, which is completely understandable that you have very packed column with very small size. So in order to get the liquid or the mobile phase to diffuse through this very packed column, you would need higher pressure. The type of station phase that we used is the highly pure and spherical microporous particle of silica that must be permeable to the solvent. Most silica does not cannot withstand pH higher than 8. So the pH of your solutions and for your mobile system must be adjusted. You must not use something that has a high pH value. Um, there are two types of silica, the stationary phase. So there is what's called bare silica, and bare silica is a silica that has an OH on its surface, and it usually uses adsorption chromatography. So this is the solid stationary phase, which uses adsorption. And there is also the liquid-liquid partitioned chromatography in the same way we as one of the types we talked about before, where you have your stationary phase as a liquid that is covalently linked to your silica or to your solid support. So the solid support here is still silica, but it's covalently linked to the or covalently bonded to the liquid distillation phase in the same way as you can see here. So this is a pure silica, and this is your stationary liquid stationary phase here, and it's covalently linked to your solid support, which is again silica. So what about the elution process in HPLC? How does it differ from gas chromatography? Now, the elution process, we have two types of elution. We have normal phase chromatography and we have reversed phase chromatography. In normal phase chromatography, we use polar stationary phase. And normally you would think if you use polar stationary phase that the solvent or your mobile phase will be less polar. What happens is that if your solutes are polar, or your components are polar, you of course want them to be retained for some time on your stationary phase. So you tend to use a polar stationary phase. And then you start to use nonpolar or less polar solvent, and the less polar solvent will have some efficiency or some strengths to replace or to replace the solute from the surface of the stationary phase. Um, it will start first to elute the less polar component first, and then the more polar component will be eluted after that. So the eluent strength will normally be increased by increasing the polarity. So if you use more polar solvent, you will elute the more polar component, and the elution power of your mobile phase will increase. So it's a measure of the solvent adsorption energy on the bare silica in this case. The other type is the reverse phase chromatography, and this is the most common used type for HPLC. Now, the stationary phase is going to be nonpolar or weakly polar, and then the mobile phase will be the other one, which is going to be more polar. Now, if you want to increase the the strength of your solution, or sorry, if you want to increase the polarity, so if you want to increase the strength of your mobile phase, you need to reduce its polarity. So less polar mobile phase will normally have this polar one will be stronger and will elute the less polar component quicker or quickly. So in reverse phase polar chromatography, because the stationary phase is nonpolar, so the less the polarity of your components, the less polar components will be retained longer than the more polar ones. So the one that will be eluted faster will be the polar component. Remember that we also use more polar solvent or elution mobile phase here. So the more polar component will be eluted first and the less polar components. If you want to increase the strength of your mobile system, then you need to increase the polarity of your mobile phase. There are two types of elution process. There is what's called isocratic elution and there is gradient elution. So If you use only one illusion, one mobile phase strength for the whole process of your chromatographic separation, then it can be a problematic or can be a problem because not all the component will be removed from the stationary phase or displaced from the stationary phase with the same eluting system. So that means that if you use only one condition, um, this is going to be very difficult to separate all your component. And I will show you now how this is not ideal for all of your components. So one component or one condition can be ideal for some of the components, but a different condition can be ideal for the other ones. So we need to vary the strengths of our illusion system or for our mobile phase. So that will take us to the isocratic and the gradient illusion. So isocratic illusion means that you use a constant solvent composition. But the gradient illusion means that you continuously change the solvent composition in order to increase the mobile phase strength. So the component that will be mostly retained or retained longer on the stationary phase can now be eluted faster. This is similar to the um, temperature and pressure programming in GC. When we said in GC we need to increase, sometimes we need to increase the temperature of the system in order to elute the components which can be retained for longer, which have higher boiling point. So this is the same for the HPLC, but now we change the composition of the mobile phase. So this is an example of how the change in the composition of your solvent system or your mobile phase can change the can completely change the illusion of your component. So this is an isocratic separation of analytes with a high concentration of a solvent B up to a low concentration of the solvent B, which is 30%. So from 90% to 30% in the mobile phase. So if you look here at 90%, we are trying to separate 8 different components. At 90%, you can see that there is a very bad resolution here. The efficiency of the column is not ideal and your components are not well separated. As you reduce the concentration or reduce the strength of change the component of B. Now you're increasing the changing the strength of your mobile system. Then you will see that the separation is become better. Now, as you go along, you can see that how they become much better until you reach to the 30%. So all the components are separated individually, but again, so the first three are separated reasonably at reasonable time from 5 to 10 minutes or 9 minutes. But then as you move along, you will find it takes a very long time. So at this point, after you finish separation of the first three components, it's better to increase the strength of B now in order to increase the to make the illusion of the other component faster. But if you move directly from 30 to 90, then you will see that components from 4 to 5 and to 8 probably will be eluted all together. So the resolution will be very bad. So you need to increase it gradually. So if you increase it to 40%, you're going to see that 4 and 5 are well separated, and then you'll probably increase it directly to 50% because there is a good separation here between 4 and 5, and then maybe increase it to um, 70, so it will again separate the other ones and so on until you separate all your components. So you have to adjust the whole system and you have to try until you get the best illusion or the best gradient. So you cannot use only one system for the whole process, but you can use the gradient illusion where you increase the strength of your mobile phase gradually. The other type, there's another type of elution process called the hydrophilic interaction chromatography, or HELIC. So hydrophilic interaction chromatography is used when you have molecules that are too polar to be retained by the reversed phase columns, because reversed phase column we use nonpolar columns, or it will be very strongly retained by the normal phase column because they are very polar, and the column is polar as well for the normal phase columns, but the solvents here is non-polar or less polar, so the very polar ones will not be displaced. So the hydrophilic interaction chromatography, in this case, we still going to use a very polar stationary phase, because they are polar molecules, and we want to retain them on the stationary phase. But the change here is going to be in the mobile phase. So the mobile phase is going to be polar as well. And the polar mobile phase here is going to be acetonitrile mixed with aqueous buffer. So it's acetonitrile and water. And then if you want to increase the strength of your mobile phase, you need to increase the component of the composition of water. So you start off with a high component of acetonitrile from 97% volume per volume percent of acetonitrile in water, and then you increase the amount of water, or decrease the amount of the acetonitrile, so it becomes much polar, and then it can displace the polar component from the stationary phase, so it can elute the very polar component from the stationary phase. This is called the hydrophilic interaction chromatography. Finally, the detectors in HPLC. We also use various types of detectors in HPLC. Again, the most common one is probably the mass spectrometer. So HPLC MS is a very commonly used one as well. The ideal detector to be used in HPLC must have sensitivity toward solutes over mobile phase. We wanted to have much better sensitivity to the solutes, not to the mobile phase. And it must have low cell volume to minimize the memory effect. It must have a low detector noise, low detection limit. Of course, we need a low detection limit, and it's better to use detectors that have low detection limit, so we can detect the smallest amount of our solute. And finally, it must have a large linear dynamic range. So now we come to the end of our topic in chromatography. And as I said, I'm going to leave a video for you about the HPLC and its component, and also about the GC. And so please try to watch this video to familiarize yourself with the different component of the both instruments and how